Hello everyone. In this lecture I'd like to do something a little bit bold and venture out towards the sociology of physics by looking at the narrative of special relativity as introduced by Einstein in 1905. This is a very foundational aspect of modern physics and has reconfigured our conception of the physical world and our place in it. And it's also notoriously challenging for ordinary people to wrap their heads around the sometimes remarkable or seemingly remarkable statements that follow from special relativity, even though it's in some sense mathematically not that sophisticated. Now, Albert Einstein is a towering figure that has dominated 20th century physics, and he was responsible, of course, not just for special relativity, but also for the general theory of relativity, which is even more remarkable. Also, he played a key role in the development of quantum mechanics and got a Nobel Prize for unraveling what was going on with the photoelectric effect. So today we're going to look a little bit critically, a little bit skeptically at this story, not with a view of diminishing Einstein's pivotal role in the story, but rather in bringing forward the role of someone else. There's another key figure here which really cannot be excluded from this story. And that, as we'll see, is Galileo Galilei. And I'm going to paint an alternate picture, an alternate story about what special relativity is really about that has at its heart the idea that it's really Galileo who first put their finger on the essential idea, and that in some sense special relativity could have been developed any time since Galileo, just by people looking carefully at the remarkable consequences of his invariance principle. So we're going to be looking at all of that today. But a good place to start is with the standard story that starts with Einstein's 1905 paper. So his treatment rests on two postulates. And the first postulate is this one here, and this is copied verbatim from the 1905 paper. So let's see what it says. It says that the laws by which the states of physical systems undergo change are not affected, whether these changes of state be referred to the one or the other of two systems of coordinates in uniform translatory motion. That's Einstein's first postulate for this new physics. And this is his second postulate, which is also taken verbatim from the 1905 paper. Any ray of light moves in the stationary system of coordinates with the determined velocity c, whether the ray be emitted by a stationary or by a moving body. Hence, velocity equals light path over time interval, where time interval is to be taken in the sense of the definition in section 1. So he's talking about the speed of light, the velocity of light, as determined in a so-called stationary system, comparing the speed as emitted by a stationary body and by a moving body, and saying that these two things are the same. So now I just have to briefly review the setup that he introduces in section 1 to support this statement. So here's a simplified version of Einstein's stationary system that he's describing, just in one dimension. Okay, the idea is already there. So we imagine that we have some uniformly spaced points, one dimension, perhaps with rigid rods separating these points. And at each one of these points, we have an observer with a clock. And these clocks are, in some important sense, calibrated with the base clock at point A, let's say. Okay, so there's a distinguished clock there, and these other clocks are coordinated with them. So Einstein recognizes that we can't just quickly assume that all these clocks are showing the same time. We have to be more precise about what that means. And he does that via a system of calibration. So he supposes, say, that we have a particular clock at B, say at the position 6, and we are inquiring, what does it mean to have this clock here calibrated with this one here? Well, if a light signal is sent from A at time, say, t sub A, and it's received by B at some time t sub B on his clock, okay, and then that light is reflected back to A and arrives at A at, say, t sub a prime. Then we want that the separation between t sub b and t sub a should be the same as the separation between t sub a prime and t sub b. And another way of saying that is that the value t sub b is just the average of the values t sub a and t sub a prime, that a reads the time of the emission of the light and the time of the light being received. So t sub b should be exactly halfway between those two. And if that's the case, not just for A and B's clocks, but for all of the clocks, then we have a calibrated system. And this is in this topic called an inertial frame or inertial reference frame. And it's a kind of a foundational sort of set piece that's used all the time. It really has its origins back in Newtonian mechanics because it's very similar in some ways to the Newtonian system, which supposes a pre-existing world in which there's a God-given spatial coordinate system and a uniform time system that's the same everywhere in space. So what we have here is such a rather rigid system, but it is from the point of view of an observer A, and we admit the possibility that we might have several of these things moving with respect to each other. So we can imagine having a second reference frame moving uniformly with respect to this one here. Okay, so now what is the content of Einstein's second postulate? It is that if we measure the speed of light, say in this system here, so for example, if A is interested in sending a light signal out, and let's say it's sent by A being stationary, and then it's recorded when that signal gets to B. Okay, so then we can take the distance or the displacement traversed, in this case 6, and divide by the time interval. So for example, if A sends out a signal at his time 0 and receives the reflected signal, let's say at time t equals 10, then halfway there is 5. And so he would say that the velocity is the displacement, which is 6, over the time elapsed, which is 5. Okay, so that's how that light velocity would be calculated in this rigid framework with these calibrated clocks. And what Einstein is postulating here is that this reading that we get does not depend on whether the source of the light is stationary, like at A, or whether it's the result of a moving object emitting light. So if we had something moving like this, and when that moving thing got to A, it emitted this light, then we would have exactly the same velocity read. Now, is this familiar to us? In fact, it's very familiar to us because that's how sound propagates in air. Okay? The speed of sound in air is independent of the motion of the object which emits the sound. If I'm moving in this direction and I make a yell, that sound is not going to go faster on account of me moving quickly in that direction. It's the same thing with a water wave. If you drop a stone in a pond and watch the water ripples go out, it's a water wave, and you measure the speed, that's not going to be any different from the water wave caused by something moving through the water and sort of abruptly stopping, and then the wave carries on. So in this sense, Einstein is saying the velocity of light here is behaving a lot like the velocity of sound or a water in one of our familiar medium, air or water. So in opposition to that is the idea of, say, firing a bullet. Okay, there's a big difference between firing a bullet from a stationary position and recording the speed of the bullet, or firing the bullet on a moving train. If I'm on a moving train and I fire a bullet in the same direction as the train's moving, then the cumulative velocity of the bullet with respect to the ground is going to be greater. So light is not doing that. It's rather doing what sound waves and water waves do in a familiar context to us. So those are the two postulates that Einstein started special relativity with. And then what he did is he took these two postulates and made some deductions and was able to derive what are called the Lorentz transformations. And these are equations, which I'm not going to tell you what they are, but they're just equations that relate measurements from one observer, like one of these inertial reference frames to another inertial reference frame moving at some velocity with respect to the first one. So the stationary one is going to make measurements of events. Something happens over here. Where does it happen? When does it happen? The moving frame is also going to make measurements about that same event. Where does it happen? When does it happen? And the Lorentz transformations explain to you how to go from one of those to the other. And those transformations had been discovered prior to Einstein due to Lorentz, and also a mathematician, Poincaré, was involved in that. But in any case, these transformations have the remarkable consequence that it then appears that if, say, the moving frame is going very fast, close to the speed of light, then strange things start to happen, such as the rulers in the second frame of reference, the moving frame of reference, appear to be shortened from A's point of view, from the original point of view, from the stationary point of view. And the clocks on that moving frame appear to be going slower. And also, in some sense, the mass of that frame or objects in that frame appear to be getting larger, although the story on that has evolved over the years. But symmetrically, curiously, exactly the same thing is happening when we ask the moving observer, quotes, to describe what's happening to the stationary observer. So from the moving observer's point of view, they are stationary and the other one is moving, and they will say exactly the same things, namely that the rulers on that former system are being shortened, and that the clocks are slowing down, and that the masses involved seem to be getting bigger. So it becomes very non-intuitive, and people had a hard time getting their heads around it. And in fact, there was a joke that very few people really understood special relativity, and especially general relativity. But with the eclipse in 1919 and sort of the confirmation that Einstein's general relativity was correct, well, then suddenly everybody sort of said, okay, this has to be the true story. And then it became really interesting to try to understand what was going on. And even today, if you look on the internet, you're going to find a lot of discussion on these things. And often the question arises, so this shortening of rods that A sees, or the slowing of clocks that A sees, is that really happening? Or is that an observational effect? Okay, that's a pretty interesting question. And what do we actually mean by those things? That's a question that I have a different answer to most expositors. Okay, so I'm more inclined to say that those things are observational effects. Okay, that if we're going to assign proper meaning to the various words involved, we end up realizing that in fact there's nothing magical at all happening in that second reference frame. It's just a question of what appears to be happening as a consequence of the way we measure things. And even more remarkably, perhaps, that it turns out that the speed of light is not at all so crucial in this story as it may at first appear. But before we get into that, let's have a fast forward to modern times and see how these postulates are viewed these days. So they're usually stated in a little bit more concise form and with actually a subtly different meaning. So if we look, say, in Wikipedia, under the postulates of special relativity, we find this form of the postulates. So the first postulate is that the laws of physics take the same form in all inertial frames of reference. And by the way, an inertial frame of reference is a frame of reference like I've described, which is not accelerating in an obvious way. So if you're being accelerated, or if you're in a gravitational field, you're going to feel sort of some force of acceleration, right? You can be able to tell. Otherwise, if you're just in a spaceship, which is just moving at uniform velocity with the engines off, you're all going to be floating around the cabin. You're not going to feel a pull to one side or anywhere else, right? So that's an inertial frame. Okay, and the laws of physics are taking the same form in all of those frames, which are sort of not being accelerated. And the second one now is more clearly focusing on the speed of light being constant. The speed of light in free space, like a vacuum, has the same value, c, in all inertial frames of reference. And in fact, the value for c is this famous number that probably every physicist has memorized. 299,792,458 meters per second. That's meters per second. That's pretty fast. So it takes like about 8 minutes for light to get from the sun to Earth. In contrast, the speed of sound in air, well, which depends a little bit on the density and the temperature and so on. But let's say roughly it's 340.27 meters per second. And obviously there's a big difference between these two things because this one's a lot faster than this one. Okay, a lot faster. But there's also another very important and interesting difference between these two things. And I wonder if you can see what that is. Maybe I'll leave that with you. There's a really interesting difference between these two values. Okay, so these are the forms of the postulate. You might say, well, this is quite different. This second one is quite different from Einstein's because Einstein was talking about what happens if you measure speed of light in a fixed stationary reference frame. And he was talking about the difference between light being emitted from a fixed source and light being emitted from a moving source. But it was all with respect to this one particular given frame. So are we morphing Einstein's original postulate here? Well, in this book here, which is The Meaning of Relativity, written by Einstein, first published 1922. Okay, so this is almost 10 years after the general relativity, so it's more than 15 years after special relativity. So he talks about this, and he's talking about this second postulate, and one area that I found here, he's referring to the following. He's talking about the Maxwell-Lorentz equations, having proved their validity in the treatment of optical problems in moving bodies. And he said the consequence of the Maxwell-Lorentz equations, that in a vacuum light is propagated with velocity c, at least with respect to a definite inertial system k, must therefore be regarded as proved. According to the principle of special relativity, we must also assume the truth of this principle for every other inertial system. So this is kind of like a bridge between his original postulate and this one here that we find in Wikipedia. And he's sort of saying that, well, because of the importance of light having to do with the Maxwell-Lorentz equations, that the first postulate, that the laws of physics are the same in all reference frames, really is then telling us that different reference frames ought to measure the same speed of light. Now, I don't exactly understand the logic of that entirely, okay? Because even if the laws of physics are the same, what we're talking about here is the measurement of some particular phenomena, okay? And a measurement very well, first of all, depends on the units that you're chosen. That could very well, most likely, is going to be different for different inertial reference frames. And it may very well also depend on other factors that are different. So I don't see that we can just sort of say that you're going to measure anything, anything out of the world, and you're going to get essentially the same answer in different inertial frames. I mean, that's obviously not going to be the case. So then you have to argue, well, what's special about light that sort of makes that argument apply? So there's a question about the bridge between Einstein's original postulate and this one here. And before I go, let me answer the conundrum if you figured it out already here, the difference between these two things. So this thing here is, you can see it's approximate. This is the result of a measurement. Somebody makes some experiments and set things up and deduce something. And so there's a decimal point here with 0.27, suggesting in the usual scientific fashion that there's some potential error. Okay, it's sort of good to 2 decimal places, but after that we're not sure. Okay, so this is not an exact measurement. This is just an approximate measurement, like most measurements in physics are. Over here, there is no approximate sign. There's an equal sign. And crucially, there are no decimal places. There's no decimal point with a couple of extra things. This is spot on. It's spot on. This is exactly the speed of light. It's 299,792,458 meters per second on the dot. And you might say, well, wait a minute, how can that be? How can that be? Well, the only way it really can be is if it's a definition. It's not the result of an observation. It's the result of a definition. So the story here is that the meter, which of course is the central sort of linear measurement in the metric system was introduced in the French Revolution. And the idea was to pin this down to the geography or geometry of the Earth. And if you take a great circle through the North Pole, okay, and you take 1/10,000,000th of the circumference from the North Pole to the equator, okay, then that should be a meter. And then after that, at some point, there was an actual physical meter stick that was kept in Paris somewhere, and that was the universal sort of standard, and people would go there to measure their meter sticks, and that was the thing. Okay, so but eventually, actually not that long ago, maybe 50 years ago or something like that, they decided that they were going to pin down the meter rather with something a little bit more physically meaningful than a rod. So there was an original thing in terms of some krypton wavelength, but ultimately it became defined in terms of the speed of light. Okay. In terms of the speed of light. Okay, so definitely we're assuming here that the speed of light is a legitimate universal constant. Okay, and then we're saying, okay, so then we're going to define the meter, so it's exactly this. So this number here is chosen so that the definition comes out to be as close as is reasonably possible to the original meter stick, but now it's defined in terms of the speed of light. But notice that now there's a kind of a curious circularity that potentially is around here, right? Because now if we talk about measuring the speed of light, well, if we've defined our displacement units in terms of the speed of light, then it's not going to be a surprise that, you know, we're going to get something that's invariant. So there's definitely something to scratch your head about here in terms of the setting up of the units with respect to this claim that the speed of light is the same in all inertial frames of reference. I mean, somebody could happily argue that this is not really a postulate. This is just an obvious tautological consequence of this definition. Okay, so the logic is that in the 1905 paper, Einstein introduced these two postulates, and then he made some deductions based on those postulates and was able to derive the Lorentz transformations and these various curious consequences like time dilation, length contraction, and so on. And that was in the 1905 paper. Interestingly, relatively shortly after, 1910, W. Ignatowski, a Russian physicist, shows that for Einstein's arguments, in order to derive the Lorentz transformations, postulate number 2, the constancy of the speed of light, is actually unnecessary. It's redundant. Okay. And this is then confirmed in a year later, or maybe the same year, by German physicists Frank and Rothe. They show the same thing, and you can actually have a look at an English translation of their paper. It's called On the Transformation of Space-Time Coordinates from Stationary to Moving Systems. That's available on the internet. So there's something curious here about the logical structure. Einstein's argument is perhaps not really tight. This second postulate, which is so important, it seems, is actually unnecessary to create special relativity. So you might have thought that this is going to be a major shift in the direction. But curiously, the physics community seems to have completely ignored this fact. And now in all textbooks, you see the same story, that special relativity is a consequence of these two postulates. So there's some interesting sociology going on here. I'm outside the discipline. I'm just a mathematician, but there's some interesting questions to be asked about what's actually going on with this story here. But in fact, there are even more serious issues with this standard story of special relativity, which has now been entrenched in the undergraduate curriculum in physics courses. So the first really serious fact, okay, is that postulate 1, Einstein's first postulate of special relativity, is nothing but Galileo's invariance principle. Nothing more, nothing less. Actually, maybe it's a little bit less, actually, to be honest, okay? So Galileo, almost the founding father of modern physics, great Italian physicist, mathematician, astronomer, discovered the moons of Jupiter, redesigned the telescope, was really one of the first people to advocate strongly the importance of empirical observation to understand the world. And he was, famous for looking and seeing that the acceleration of different masses of bodies are the same, dropping things from the Leaning Tower of Pisa. He was interested in projectile motion and showed that the trajectory of a particle, if it's a ball that you throw up in the air, is a parabola. Okay, so that's a conic section. He was involved in all kinds of things, but crucially, he was actually responsible for this. And this is so important, okay? So I have to read this to you, and this should be mandatory for all students of physics, okay? You should not be able to get a degree in physics without having read this paragraph, which in my view is clearly the most important paragraph in the history of physics. Nothing else comes close. So it's a quote from Dialogues Concerning Two New Sciences, in Italian, Discorsi e dimostrazioni matematici intorno a due nuove scienze. Published in 1632, okay, Galileo Galilei. He was the giant upon whose shoulders Newton stood, okay. He writes, shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the little animals fly with equal speed to all sides of the cabin. The fish swim indifferently in all directions. The drops fall into the vessel beneath, and in throwing something to your friend, you need to throw it no more strongly in one direction than another, the distances being equal. Jumping with your feet together, you pass equal spaces in every direction. When you have observed all these things carefully, though there is no doubt that when the ship is standing still, everything must happen in this way, have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. That last sentence is so important, I have to repeat it. You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. This is the same as the Wikipedia statement that the laws of physics take the same form in all inertial frames of reference. So there's some serious questions to be asked here. First of all, does Einstein credit Galileo? No, he doesn't. Does Wikipedia credit Galileo? Not that I can see. Why is it not the case that Galileo, who was not an insubstantial figure in the history of science, okay? This is like a main dude, okay, at the height of his powers, and he's out there forging boldly ahead. There's no way you can ignore what he's saying. So why is it that the story that we're told over and over again about special relativity and Einstein's postulate, why isn't that acknowledged to be actually Galileo? There is some interesting sociology here that, if you're a physicist, you should think about it. You should think very deeply about it. Okay. I don't think it would diminish Einstein's reputation too much. Einstein is a towering figure, independent of his development of special relativity. And even if you take a little bit away from that, he's still a towering figure. But we don't have to have some godlike reverence for him and not be able to admit that actually the main idea here actually belongs to Galileo. And so that's a really important point. We're going to come back to that. But now the second one. Both postulates, in quotes, are actually rather hypotheses. They're not postulates. There's a very big distinction between these two words, and we need to be careful about the usage of words. A postulate is a statement which is self-evident, which is obvious, which we can all accept without prior demonstration. For example, the postulates of Euclidean geometry. Those were the standard well-known postulates. That say you have 2 points on the plane, there's a unique line that passes through them both. Okay, that's a postulate. It's an obvious fact. Can you prove it? Well, you could say, I don't know how to prove it. I mean, it's obvious, you know. You can prove it if you have a prior algebraic setup in terms of Cartesian geometry, and you've defined points and lines algebraically, then you can prove something like that. But if you just have a geometric orientation, it's a standalone thing, okay? But the postulates of special relativity are not of that kind. They're not at all of that kind. They are statements about the world, which are not obvious statements, and which a priori could be true or false. So they are statements that have to be viewed in the lens of hypotheses, and we should look for verifications of them or repudiations of them based on empirical observation, as we do in science. So if you're going to say, oh, the laws of physics take the same form in all inertial frames of reference as does Wikipedia, you have to acknowledge that's not a postulate, people. That is a hypothesis. That is a very strong hypothesis, in fact, and really ought to be subject to all kinds of attempts at verification. But unfortunately, it's a little bit hard to do because, you know, we can get a spaceship, but can you get a Klingon spaceship, you know, going at warp 7 above us, and we start communicating with them and performing the same experiments and seeing if we actually get the same results? That's not so easy for us to do. But that doesn't mean that we can or we are allowed to, you know, pretend that this is not a hypothesis, that it's just something that we can assume. No, we can't do that. And it's the same thing with the postulate number 2. Okay, that's not a postulate either. That's obviously a hypothesis. That if the Klingons measure speed of light in their spaceship and we measure the speed of light, we're going to get the same answer. Well, maybe we are, maybe we aren't. Let's talk to some Klingons and see, or let's set up an experiment where we can actually do that. It turns out that measuring the speed of light actually sort of, you know, honestly and accurately is hugely problematic, in fact. So that's no easy thing to do, okay? Most measurements of the speed of light are not really measurements of the speed of light. They're measurements of the two-way speed of light. You get some mirror and you bounce something off and you wait till it comes back, okay? That's not really the same as a one-way measurement. Like me trying to, you know, measure how fast Usain Bolt runs 100 meters. You know, so am I going to run with him? Here's a stop. I have a stopwatch. Okay, go. Okay, and then I'm going to run with him to get to the finish line at the same time so I can click again and see how far he's gone. No, I can't do that. So what I'm going to do is instead say, Usain, please, you're going to run to the 100 meters and come back. Again, I'm just going to sit here and record, start and final time, and then we'll divide by 2. Is that accurate? What about the turnaround? Does that figure somehow? Maybe he goes faster one way than the other, etc. By the way, I should also mention in terms of Galileo, that quote that I told you about, right? Galileo is clearly not giving his principle as a postulate, right? He is voicing it as a hypothesis and in fact indicating a pathway to verification. He's not saying, oh, you should just believe this. He's saying, here's what you need to do in order to verify this principle. Okay, employing this basic underlying, direction of science that we should actually go and measure things and check that things are true empirically, not just armchair theorizing. Right? So actually, Galileo's statement of the first postulate is superior to Wikipedia's, in my view, because it makes it clear that this is a hypothesis that needs to be checked. So that's I think a really interesting point. How can the sociology of science be such that these two foundational things are regarded as postulates? To me, it's a little short of incredible. Okay, but now we come to the really serious one, people, okay? Which I'm going to have to talk about in another video, but it's that the second postulate is either wrong or meaningless. In actual fact, okay, there's something seriously problematic with the idea of the speed of light as a universal constant. And so let me just give you an initial orientation how to think about that. So let's go back to Galileo. And let's imagine not ships on the ocean, but spaceships, okay? So we're in a spaceship and we're floating along. The engines are off, so we're in an inertial frame of reference, at least a small one. And there's a Klingon ship up ahead. Okay, it's coming this way, fast warp 7 or whatever. And let's suppose that there's a piece of space junk, okay, that's coming towards us. Yeah, it's a ball bearing, let's say, okay? So it's a ball bearing. So let's have a look at this ball bearing, okay? And let's ask the question, what's the velocity of that piece of space junk, of that ball bearing? If you read Galileo and you think about it, you realize that that question is a meaningless question. The answer to that question is, sorry, that's a meaningless question. Because it's impossible to assign absolute velocities to anything, not even to yourself. You can't tell whether you yourself are stationary or are moving with respect to some speed. Similarly, you can't say whether the Klingon ship is stationary or moving with what speed, and you can't tell whether the piece of space junk is moving. So strictly speaking, okay, and this is a line of argument that anybody could have done, hundreds of years ago. Velocity of an object just by itself, is not a well-defined notion. Therefore, momentum of that object is not a well-defined notion because momentum is mass times velocity. Also, kinetic energy is not well-defined. 1/2 mv squared. You don't know what v is. V is meaningless, so kinetic energy is meaningless also. So you see that adopting Galilean ideas, okay, immediately gives you strife with Newton's laws, because now the basic Newtonian mechanics is all of a sudden in very shaky territory. And the concepts that we thought we understood really well in Newtonian mechanics back in high school or maybe first year university, actually we were probably kidding ourselves. Okay, those are just they may be very practically useful, but they are not. They're not really fundamentally connected to the way the world really is. Okay, so that's giving you some kind of idea about why this second postulate is wrong or meaningless. I mean, if you can't tell what the velocity of a ball bearing is, if you have an electron going by, well, it doesn't make any sense to ask what's the velocity of that electron either. And if you have a photon going by, why should that make any more sense? You can't measure the velocity of anything, okay? You can't measure the velocity of anything. And even if you did, even if you were somehow, you could say, well, oh yeah, but I can measure it with respect to myself. Fair enough, as long as you have a specified unit system. So you can specify an observer and a unit system, and then you can make some local or relative measurement. Okay, but the Klingons up there going vastly different speed, and notably with a different set of units, they're going to come up with a completely different reading to this local relative velocity. You are not allowed to assume that the Klingons are also operating with meters and seconds, which seems to be a common kind of thing that modern discussions of physics seem to do. Okay, so we're going to talk more about this. This is hugely important and sheds a big question mark on a lot of modern exposition of special relativity. So this narrative really ought to be rethought in a way. And we should also examine the sociology of it. How is it that we've been kidding ourselves all this time? I'm J Wildberger. Thanks for listening.